Okay, so hi everyone. Okay, so we continue the review as so this is the third review. We will have one more on Wednesday, and then that's it. So I'm just thinking, should I ask Aftab to give extra review sessions or not? I don't know. If you think it's needed, just let me know if you think. Okay, so who's going to ask the first question today? No questions? I can mention a couple of other topics. We already discussed some topics, I guess, on Friday that turned out to be important, will be important. So maybe today I will start from somewhere else. I think one of the things we discussed was arc length. Curvature. So remember, one of the things we did was this arc length parameterization that we discussed. Maybe we visit this issue again. So what we have is a curve, R of t. So t is in some interval b, a. So we have like this interval in the line, right? And this is a map, R, that takes this piece of line, the interval AB. You can think of time interval, for example, or some parameterization interval, it doesn't matter. You go to three-dimensional space. You can go to two-dimensional space also, it doesn't matter, but in general, we go to three-dimensional space. So you start from point here, R of A, and then you go on, and then you reach to a point which is R of B. So we discussed that this is the idea of the curve. Now, one of the subtle things about this situation is this. The curve is this geometric image, right? The curve is that geometric shape, but this equation, R of t, for example, we write R of t equal to x of t, y of t, z of t. This is just a parameterization of the curve, right? So we have to distinguish between the two. This is not a primary concept. The parameterization is not primary. What is primary is the curve itself. So there is a subtlety here, right? There's an idea here that we have to come to terms with. What I'm saying is that you can have a different parameterization and still get the same curve. That's quite possible. You can have another parameterization, for example, from some other interval CD, some other curve, some other parameterization, so maybe R tilde of t, which would be x tilde of t, y tilde of t, the tilde of t, right? But then what happens is that you exactly get the same curve as a result of working with this new parameterization. So we have to distinguish between the parameterization, which is a secondary concept. It's just a tool, it's a convenient tool to talk about the curve. But the geometry, the curve itself is this. It never changes, it's there. This will change. So one of the things that we define for such curves, we use the parameterization to define it, this was length, right? Length of curve was equal to integral a to b square root of, so that was like norm of r dot of t, right? This was one formula. This was the derivative of r dt, which is really nothing but integral from a to b square root of dx dt squared plus dy dt squared plus dz dt squared dt. So if we have these three functions, x, y, z, we can go on and compute this quantity. This would be. But then one of the things that I emphasized maybe during the lecture, maybe I did not emphasize enough, is that this length really just depends on the curve and does not depend on parameterization. So if you change the parameterization of the curve, you will get the same number for the length. Why is that so? I mean, the reason is that intuitively we understand that length is some geometric concept, should not depend on how you traverse your curve. If you're going fast or slow, for example, along the curve. Going fast or slow, with what velocity, what acceleration, is a question of physics. It's not a question of geometry. So there is something subtle going on. Okay, so then as a result was that we said there is a parameterization, which was arc length parameterization, which is the kind of most favored parameterization of the curve. It's the best parameterization, is kind of canonical parameterization of the curve. And what was that parameterization? To obtain that, we define this function from here. So we define S as a function. So we define S of, say, t to be equal to integral from a to t norm of r dot tau d tau. So this function now is a function of t. Okay, so the way it works is that we have this interval AB. We have the interval AB to we have this interval AB, and then we have moving to 0 to L. L is, this is equal to S of B, obviously. If I put T equal to B, I get A to B, which is this one. So S of B. Now remember what this S function does. The S function picks a value here and gives the length of the curve from A to T, just up to here. So this is R of T, for example, right? So then as a result, takes this interval AB and stretch it or shrinks it, depending on, and then move it to the origin from interval to interval 0 to L. Okay, that's the canonical thing. And then what we said is that we are going to invert this function to find S in terms of T. So this S of T here, find the inverse function. So this inverse function would be T equal to T of S. And then once you find this function as a function of S, you replace T by T of S. So you just say R of S equal to R of T of S. And this is the arc length parameterization. So This is arc-length parameterization. So this is a rather subtle idea. I mean, again, everything here we discussed today is rather subtle. So we have to be parameterization. We have to be a bit careful with these things. And of course, the success in doing this problem depends on if you can calculate this integral successfully, and then you invert the function successfully. Then you can write down the arc-length parameterization. So this arc-length parameterization was useful when we defined curvature, we derive formulas for curvature. So let me give you an example now if you don't have a question. Okay. So have these pictures in mind. This is very useful. So here's an example. I'm going to give a simple example so that you can just see what's going on. So find the arc-length parameterization of the curve okay, R of t equal to 2t plus 1, t minus 3t, and t plus 2. So t is going from 2 to 1. Okay. So a curve is given like this, 2t plus 1, negative 3t, t plus 2. T is between 1 and 2. And we are supposed to find the arc-length parameterization of this curve. Okay, so there is a question. T equal to 2ts. So shouldn't R of t of s rather than R of s equal to R of t of s? No, it should not be R of t at the end. You see, at the end, what you find is a function, should be a function of s. So if you write R of t again, means that you are defining a function of t again. We have a function of t. We want to write in terms of function of s, right? So we just write R of s. I mean, it could be a different function, but just write it as R of s equal to R of t of s. You may want to write sometime R tilde, but your book actually doesn't write R tilde. It just writes R of s. So that's why this is useful notation because it's just not very cumbersome. Did you get the point? Okay, thank you. Good, yes. Let's do it then. So now in this case, let's compute this integral then. Let's compute the integral. So in this case, we have got, so remember, we always compute s of t first. So s of t is equal to integral from 1 to t norm of r dot tau d tau. Don't write t here, right? Because if you write t here, it means that we don't know the meaning of integration notation. Integration notation, this t is in the upper limit. So this t should not be mixed with the variable of integration. That's important, right? So we have to separate the two things. So this is correct. This is tau. This is t. They are different. And this is derivative. So s of t then is equal to integral from 1 to t. So now let's compute our prime of tau. So this is our prime of t is equal to 2, -3, and 1. So that's really a lucky situation because this turns out to be equal to independent of t. This is even independent of t. It's just a constant vector, right? So we have got 4 plus 9 plus 1 d tau. Okay, so s of t is equal to integral from 1 to t then. Root 10, 14 d tau. Okay, so this is equal to, well, antiderivative of root 14 d tau is root 14 tau, but we have to integrate it between 1 and t. So that's equal to root 14 times t minus 1. So this is s of t. This is the function s of t, which is root 14 t minus 1. Okay? So now we have to go and find here t as a function of s. So we have to invert this now, right? So next step is we have to invert this function. Or in other words, we have to find the inverse function. So how do we invert this function? How to invert this? So s of t, or so I just write s is equal to root 14 times t minus 1. So we have to solve for t in terms of s. So solve for t in terms of s. Okay, you divide, you get s over root 14 equal to t minus 1. So here you get that t is equal to s over root 14 plus 1. That's t. So t turns out to be equal to s over root 14 plus 1. Now what we have to do, as a last step, we have to sub in t in the original parameterization by this function. So this is the last step. Last step is this, sub in t by s. Okay, so the equation for the line, for this curve was remember the equation for the curve was r of t. What was it? Do you remember? It was like 2t plus 1. I guess, was it, what do you remember? What was it?
Yeah, it was 2t plus 1.
2t plus 1?
Negative 3t.
Negative 3t.
T plus 2.
And then t plus 2, right. Okay, so then r of s is equal to 2 times, now we have the value of t. S over root 14 plus 1, so just sub in times s over root 14 plus 1, and then plus 1. Don't forget to write this plus 1, that's important because it's here. And it's not affected by anything, it's just there, it's a constant. Next term would be negative 3 times, again, the value of s, s over root 14 plus s over root 14 plus 1, and comma, I like the last part here, t plus 1, t is s over root 14, right, plus 2. Okay, that's it. But then we have to write what is the range of s.
Yes. Plus
Oh, here?
So you added the +2, but you forgot the +1 when you subbed in the t.
Oh, here I should have +1 here, you mean, right?
Yeah.
Right. So if I have +1, +2 makes it +3 in this case, right? That makes it +3. Sounds good. Okay, very good. So now one thing we have to add is to put the range of S. So where S changes. So S would be between what and what values? Well, on the left-hand side, it's 0, because when you start at the starting point of the curve, length is 0. That's the nice thing about this parameterization. It always starts at 0, because at the beginning, there is no length. It's 0. But then when you go at the end of the curve, the full length of the curve will be given. Now, what is here? So this would be L. L is equal to, well, the parameterization was between 1 and 2, I believe, right? So if I just put here 2, would be root 14. Was it between 1 or 2 or 1 or 3?
1 and 2.
1 or 2, okay, thank you. Okay, so that's okay. So S is between root 14. 0. So this problem was rather easy. In fact, if you know the kind of mechanics of the problem, it was easy because the integration turned out to be easy. And the reason, by the way, this integration turned out to be so super easy was because we just had a straight line. So we just had a straight line from some point to another point. But that this parameterization, the guy who was traversing this curve was traversing it with a kind of special speed. I mean, like root 14, 1 over something like that. With root 14 speed, so it was traversing it faster than the length, and also it chose the initial time to be 1, not 0. So there was a shift of time, and also there was a shift, there was a speed which was changed. But the right parameterization, which would be the length parameterization, is this. Okay, so I have a question again. How did you know it was square root of 14? Okay, yes. How did I know it's the square root of 14? Well, you see here is 1 plus 9 is, so you're okay with this. And here I replace t by 2. Because at the end, you reach the end when t is equal to 2. Because the parameterization was t between 1 and 2. The right extreme point is 2. So when you put t equal to 2, 2 minus 1 is 1, then only root 14 remains. So this is it. Is that clear now? Okay, excellent. Yeah, very good. Right, no, I mean, this is a kind of nice type of questions about arc length parameterization. So it was like a two question in one question. We had to, actually several questions in one question. We had to know the formula for the length, how to compute the length of the curve, but then how to invert this function, what is arc length parameterization. So there are several questions packed in one. So this was a nice one. Okay, so another, if there are no questions about this, maybe I'll go to a topic which is quite related to this, that is the idea of curvature, and we recall that and maybe give some examples of that. All right, so yeah, this is our plane parameterization. Okay, so let's go to curvature. Right. So curvature. So again, we had like a curve R of t. So some t between one. Sorry, between some b and a in general, in some interval. So we defined some quantities that moved along this curve, right? So one of them that you remember we defined was unit tangent vector, right? T of t was unit tangent vector. So at each point, it was in the direction of the velocity, but it had length 1. It's normalized to length 1. So this was equal to, by the way, this is equal to r dot t. Did I use notation r dot before actually in this course? Or I used r prime?
Yeah, I used prime.
R prime? Oh, so maybe I should have not used r dot. R prime t divided by its length normal. So this is velocity vector divided by length of the velocity vector. So basically this is velocity divided by speed, right? Velocity by speed. Okay, this is t of t. Okay. So this obviously it's a vector field that changes, and as you move. Oh, this is not quite right. Maybe it should come here. Yeah, it would be very strange to change all. It can happen, but it could have happened, but it's kind of better to have it like that. Okay, so we have that, and then we had this normal vector also. Remember? So what was this normal vector? Normal vector was, we took this derivative of this unit tangent vector and normalized it again. So this was n of t, it was equal to n prime, t prime of t divided by norm of t prime of t. So this was called a normal vector. So this normal vector, yes, it's always orthogonal to this unit tangent vector. This t prime of t is always orthogonal to t of t. We checked it in class. You see t prime of t is orthogonal to t of t. We checked this in class. So as a result, and then n of t also is orthogonal to the tangent vector, unit tangent. Because after all, n is nothing but this t prime divided by its length. So if this vector is orthogonal, normalization is also orthogonal. So that's good. So this is also changing with, well, I mean, this is not quite length 1 really. So it's also changing with this as we go. But then there was a third vector, which was the binormal vector. Binormal vector. So this was, the notation was b of t. I think it was like t of t cross it with n of t. So these three vectors, t, n, and p, form a right-handed orthonormal frame at each point on the curve. So this was T, this was N, and this was B. So it's a frame that's changing in time, and it moves along this curve, and then it kind of dances around this curve as you move on. This works like that. Okay, so this is this one. So this is an orthonormal frame. So this sort of terminology you have to know, and you have to So by the way, this is quite easy to find, right? Because we are given, say, a parameterization of the curve, and we are asked, for example, a typical question, easy question in this case would be, find this binormal vector, for example. Well, okay, so binormal vector, you just find T, you just find N, and then you know how to do cross product, and then you've got the binormal. There is a little bit of difficulty in finding N because you have to normalize the velocity to find T, R prime, normalize it. And then you may get some extra factors here, but that's okay. But then you differentiate, normalize, and then you do cross product, which you can do. So that's not a problem, right? Okay, so that's that. Now, how did we define curvature? So for the curvature, you remember, we had several definitions, but our kind of primary definition was that curvature is rate of change of unit tangent vector with respect to arc length. We had that. So is rate of change of unit tangent vector with respect to arc length. Okay, so let me write it. Is rate of change unit tangent vector with respect to WRT with respect to arc length. So what does it mean? It means that K is equal to norm of dt ds. So in this formula, this really means we have to think of t not as a function of t, but as a function of this new parameter s that we introduced in the previous part, right? So once you write t of s, which we can, because in t of t, right, that we have here, you replace t by its s value from that change of variable by inverting this arc length function, we get this, and then you get a function of s. So this function of s is a function that tells us what is the value of the unit tangent vector at arc length s from the origin, as from the initial. And it is the rate of change of this function that we want. There is a bit of subtlety here also still, namely, we are not interested in this vector itself, we are just taking length of this vector. So that's kind of brutal. It would be nice if you could just say, okay, this would be the curvature vector at that point. But that's not what we take. We just take its length. We kind of simplify things, right? You could have taken the curvature as a vector. I mean, that's a possibility. I'm not saying exactly I know what happens in that case. Maybe it's nothing interesting will happen in that case, but that would be a possibility. But we don't look at that for some reason. we simplify things, we just take its length. It's like a vector, we neglect the direction of that vector, and we just look at the value of the length of that vector. Okay, that's fine. So this is the curvature. But this was our original point, and then we said that this is a difficult definition to work with. Indeed, it's quite difficult to work with because just imagine you have to go on and compute that arc length function, inverting things and all that. So that would be a lot of work. But then there was a magic formula that I proved. It's a well-known formula, actually. So the formula turned out to be, you don't have to go through this, through the torture of finding S and finding T as a function of S and then taking the. You can work originally with your parameterization T. So the formula that we derived was this formula. Kappa T turned out to be equal to length of, remember, r prime of T plus r double prime of T divided by length of r prime of T. Do you remember to what power was it?
3/2? Or
it's 3.
Okay.
It's 3, right, it's 3, right. I know why you said 3/2, because there's a formula which has 3/2, exactly, yeah, that's okay, very good. So we have this now, r prime of T to the power 3. And this formula is straightforward because just given any curve, you can just find. You can just compute r prime, cross it with r double prime. Right, so that's okay. So there was a special case. So this is a special case, you remember, it was the case where we had this graph. Oh, there is a question. 3, yes, that's right, thank you, yeah, it's 3 indeed, yes. So there's a question where we had the curve as a graph. Curve is given as a graph, as a 2D graph, actually. So in that case, it was like y equal to y of x. Okay, so then we said that, well, I mean, this is from interval a, b, so this is like back to calculus 1000, right? One variable, and we take its graph, makes it 2 variable. Y of x, right? So this was x, and this was y value. Okay, so, but then still this is a curve because it's in 2D, but you can see it's in 3D. So it should be captured by these general formulas. And these general formulas, when you work out in this case, further simplifies. So in this case, the curvature, okay, at x turns out to be equal to absolute value of second derivative of x, y double prime of x, divided by square root of, so let me write it like this, divided by 1 plus y prime of x squared to the power 3/2. Yeah, so that's it. Yeah. So to get this formula from that, we just said that this is a parameterization r of x equal to x, f of x, and 0. So here t was x, and this is a simple parameterization. So you follow this recipe for this parameterization, you do get this. Of course, it's better at this stage to memorize this formula because, I mean, you can derive it if you want, but you have to spend time and you may make mistakes. So it's better to memorize this formula. And you see, this is 3 over 2 because, I mean, this 3, there's already a square root sign here, so that's captured. Yeah, so there's no square root sign here. Square root is 1 over 2. Okay, so now these sort of problems are useful, and I mean, kind of can ask questions about these things. For example, let me give you a question now. Yeah, so maybe this question, I don't know if this is really feasible or not. At what point x between 2 and 1, the curvature of graph of the function graph of the function yeah y of x equal to 1 plus x2 is minimum, for example. So to start with just getting an idea of this function, maybe this is a simple function. It's a parabola that starts at 1 and goes up, right? So we're going up. And we are just looking at the values of function between 1 and 2. So this is, imagine, 1, and this is 2. So we are looking at this parabola here. And we want to know at which point, what point, the curvature of this function is minimized. For example, we want to know at what point this is maximized, things like that. These are reasonable questions, right? Okay, so what we have to do, we have to follow this recipe and then see if we can solve this problem or not. Then turn it into maximization or extremizing, actually minimization problem in this case, right? So first of all, what is the curvature? Absolute value of y double prime. Well, y double prime is very easy because this is y prime is 2x and y double prime is 2. So this is absolute value of 2 divided by 1 plus, now what is f prime or y prime? Y prime is 2x is 4x squared, right? So 4x squared. The power 3 over 2. And let's not forget that x is supposed to be between 1 and 2 only. We are not supposed to look at other points. We are just supposed to search between 1 and 2. So, okay, that's fine. So we want to know at which point where k is minimized. Well, I mean, this is a simple function. There is no variable in the numerator, right? And everything is in the denominator. So this function is minimized exactly when the denominator is maximized, right? So have to maximize denominator, which is 1 plus 4x2 to the power 2. And now we are asking ourselves the question, where this function is maximized. This function. If x is between 1 and 2, where is it maximized? Where this function is maximized?
Do you minimize because you
Yeah, exactly. It's minimized at 1, but it's maximized at 2. And we are interested in the points where this is maximized because it's 1 over. So when you do 1 over, it's minimized there. So what happens is that the curvature at this point is minimized. Okay, so let me write it formally. It is maximized at x equal to 2. So the curvature K is minimized at x equal to 2. I mean, it's not really so clear. I mean, by looking at graphs that the curvature at this point is minimal. I mean, these graphs are not realistic at all, the actual graphs. And by the way, by the same analysis, the curvature is maximized at this point. That's very funny. And K is maximized. This is not asked, but extra K is maximized at x equal to 1. I mean, in this interval, okay? 1 and 2. If you want to maximize it overall, it's going to be at 0. Again, that's also not very intuitive because when you look at the scale, it's kind of, it looks like it's flat at x equal to 2. It's kind of tangent, its tangent is parallel to, but it's not the tangent that measures the curvature. It's the derivative of the tangent that measures the curvature. And the derivative of the tangent is actually its rate of change somehow. It's what? Maximize at this point. So let me write it globally then. So this is about absolute. I mean, this is kind of local and absolute issues, right? Absolute. K globally or absolutely, I would say K is maximized at x equal to 0, and it's minimized at infinity. So this curve, as you go to infinity, becomes flat. It's again not very intuitive why it's becoming flat. I mean, because it kind of picks up, goes up, but I don't know why it's becoming flat, but it does. And is K equal to 0, which is minimum at infinity. So this stuff is not asked, okay? We should not confuse this with the solution of our problem. These are extra stuff that I just said for your knowledge and better understanding of the thing. So yeah, I mean, these formulas are very valuable and it's kind of, it gives us some intuition about it, but they are not sometimes very intuitive. I mean, one has to think hard and well about them. So, okay, so any questions or comments? Okay. So there is one more lecture, and please don't forget to go on and answer those student questionnaires. They are very important. You can express your views. I mean, department, university, myself rely on your opinion. So that's important. I'll send a note about that, post a note in all about that tonight. So, okay, guys, so see you on Wednesday. And if there are any questions, let me know. And I will send some explanations of the exam, upcoming exams. Have a wonderful day. And so let me just end the meeting. Pause.